Welcome to the Deep Dive. Today, we are undertaking a deep exploration of a document that is quickly becoming mandatory reading for pretty much every chief information security officer and software architect in the industry.
It really is.
We are talking about the draft, Critical AI Security Guidelines, V1.2.
This document is absolutely critical, and it's not just, a collection of technical recommendations. It really represents a major collaborative consensus.
Right.
You have security leaders from SANS, industry giants like Fortinet and SAP. You have researchers and policy advisors who have worked with the U.S. Congress and the White House.
So a huge cross-section of the industry.
A huge cross-section. They are all coming together to define what secure AI implementation looks like right now.
And that collaboration is exactly why we're here today. Our mission is to essentially treat this document as a masterclass. We're going to break down these complex guidelines section by section. We want to make sure you don't just understand what the recommendation is, but why it matters in the context of all these emerging threats.
And we've structured this deep dive around the 6 critical security categories the authors identified.
Okay, let's lay them out.
First, access controls, then data protection, deployment strategies, inference security, monitoring, and finally, the foundational layer of governance, risk, and compliance, or, GRC.
And the key here is that if you're building, deploying, or managing AI, you have to think of security across this entire life cycle.
Exactly, not just at the network perimeter anymore.
And the clock is ticking. Right.
Yeah.
That makes this knowledge really urgent. The authors themselves note that the landscape is incredibly fluid.
Yeah, they cite the simultaneous emergence of these huge controversial applications. You've got the DeepSeek chatbot in Hangzhou, and then the US-based Stargate AI project infrastructure.
And these were popping up while they were finalizing the document.
Exactly. Things are just moving so fast.
So that speed, it really confirms that securing AI is an ongoing adaptive challenge. It's not a one-time configuration effort.
Not at all. The recommendations we're going to talk about are point-in-time guidance. They are the absolute best practices reflecting the known threat landscape today.
And organizations are generally choosing a risk-based approach, right? They're implementing AI slowly but strategically.
They are. And our job here is to give you the operational and security intelligence to leverage those capabilities securely.
So you can minimize risks like unauthorized interactions, data tampering.
And those high-impact adversarial threats we hear so much about, like model poisoning and prompt injection.
Okay, so let's start at the very beginning of the security chain. Before the model can even think, we have to secure the environment it lives in. Let's unpack the foundational elements of security, locking down the gates.
Right.
So Section 1, access controls. This feels fundamental.
It is. We know this for traditional systems, of course.
Right.
But here, we are applying the principles of strong authentication, authorization, and monitoring specifically to 3 new, very high-value assets.
Which would be the AI models themselves.
Models, yep. The infrastructure they reside on.
And critically, the data that continuously feeds them.
And the single most important task here, what the guidance really emphasizes as the core principle, is protecting the model parameters.
Okay, why the parameters specifically?
Think of the model parameters as the distilled intelligence. It's the intellectual property that's been baked into the AI. If an attacker can get unauthorized access and modify or even just replace a deployed model, you've lost everything.
You've lost not just the investment, but you've potentially introduced untold operational damage.
Untold damage. This applies throughout the whole life cycle, but it is especially critical for those models actively being used in production.
To make this tangible, the guidelines offer a really powerful scenario. They call it the auditor agent.
Yes.
This helps illustrate why integrity, in this case, is often much more important than confidentiality.
Let's walk through that specific risk because it's a great example. Imagine an enterprise has built a complex generative agentic system. This system might be responsible for, say, reviewing legal documents or executing financial transactions. It's an ensemble solution.
Meaning it uses several components working together.
Right, including one dedicated LLM we'll call the auditor agent. This auditor agent is the critical gatekeeper. Its only purpose is to check the system's proposed response or action for safety, for alignment, and for any malicious intent.
So it's the last stop, the final check before the system takes a critical action or releases a response to a user.
Exactly. It's the final line of defense. Now, what if a bad actor, through, poor access controls, manages to tamper with the deployed model parameters of just that one auditor agent.
Just the auditor.
Or maybe they inject a hidden prompt into the system that subverts the auditor agent's function. Suddenly, that critical gatekeeper is compromised.
And it starts greenlighting things it shouldn't.
It starts approving inappropriate, malicious, or non-aligned responses. The reliability of the entire complex system is immediately and catastrophically broken.
All because one seemingly small component, the guard, was subverted. That's terrifying, because the breach isn't necessarily about stealing data in that case. It's about introducing operational chaos or misdirection.
Precisely.
So we need traditional controls, like least privilege and strong accountability, and we have to apply them to these models as if they're critical assets.
We do. But the document really stresses that traditional file permissions just aren't enough.
They're not going to cut it.
They absolutely are not. Protecting model parameters requires layers that go deeper than the file system. We must mandate the encryption of model files when they're at rest. That's table stakes.
Okay.
But when the model is loaded and running in memory, that data is highly exposed. And that's why the guidance pushes for things like runtime obfuscation and, increasingly, the use of trusted execution environments, or TEEs.
For our listeners who might not be familiar, can you elaborate on what TEEs are and why this kind of hardware-level solution is so crucial for AI security?
Sure. Think of TEEs as a secure, isolated enclave inside a processor, a vault. They ensure that sensitive computations and data, in this case the loaded model parameters and the inference process, are completely protected from the rest of the operating system.
Even from the main OS on the machine?
Even from a compromised OS. This is key for AI because it mitigates runtime model theft or exfiltration. An attacker might compromise the server the model is running on, but because the model's weights are protected inside that isolated hardware enclave, they can't be directly read or stolen.
I see. So it's a hardware-enforced boundary.
Exactly. And the authors specifically call out guidance from the OWASP AI resource on model theft, reinforcing that TEEs provide a recognized modern solution against this very specific threat.
That really speaks to the importance of moving beyond traditional perimeters. We also need to recognize that access controls are evolving to include AI systems in zero-trust strategies.
Right. Traditional security focused on static, hard-coded privileges based on user roles. You're inside the castle, so you're trusted.
The old castle and moat idea.
Yeah. And zero trust just flips that on its head. It verifies every single request regardless of its source. So as organizations migrate to zero trust, which ensures only the absolute minimal required access is granted for any action, they must incorporate AI systems into that transition planning.
So the connected APIs, the devices interacting with the models, the agents themselves.
All of it. An AI endpoint is just as much a risk as any human user, and it has to be treated with that same level of scrutiny.
And this idea of access control is especially critical in what's become the industry standard for enterprise LLM apps, Retrieval Augmented Generation, or RG.
Yes. Let's talk about augmentation data security in RG.
Okay.
RG systems are powerful because they don't rely only on the core LLM's static knowledge. They pull in fresh context from external sources.
Typically stored in vector databases.
Right, vector DBs, which are indexed semantically. But this augmentation data, this external context, is a gold mine for attackers. If it's unsecured, it becomes a huge source of risk.
And if that augmentation data is unsecured, what's the immediate result? What's the attack?
Tampering. It's all about tampering. Because that data directly influences the LLM's output, it's the context the model uses to generate its response. If a bad actor modifies the vector DB content, they can effectively poison the context stream.
So the model will then generate misleading, dangerous, or compromised responses, even if the core LLM itself is completely secure.
That's it, exactly. It's a classic man-in-the-middle scenario, but the victim is the model's own decision-making process.
So the mitigation has to be really rigorous around the vector DB itself.
Absolutely. We have to enforce least privilege access for both read and write operations on those vector DBs. Secure upload pipelines are mandatory. How is data getting into that database in the first place?
You need logging too, right?
Comprehensive logging and auditing for all changes, and strong validation mechanisms to detect unauthorized data modification instantly.
And the document pushes for cryptographic measures on this data, moving beyond just simple encryption.
Yes. Encryption at rest and in transit is necessary hygiene. It's the baseline. But the guidance suggests going a step further, digital signing of the document chunks or data segments that are indexed in the vector DB.
Why the digital signature? What does that add?
It adds a layer of provable integrity. When the LLM retrieves that chunk of data, the system can first verify the signature to ensure that the context hasn't been maliciously altered since it was originally indexed. It enhances trust in that critical augmentation layer.
Okay, so we've locked down the perimeter gates with things like TEs and secure vector DBs. Now we have to talk about what's inside the warehouse, the data itself.
Right.
Moving on to data protection. The integrity of your models, as they say, hinges entirely on the integrity of your data. If we fail here, we risk model vulnerabilities and massive data leakage.
And defending the training data is the foundational activity. This isn't just about making sure your proprietary information stays confidential.
It's about making sure the data isn't poisoned.
Exactly. Adversarial access to training data, whether it's for a giant LLM or a smaller, specialized machine learning model used for, say, real-time security decisions, can stealthily introduce vulnerabilities. It can compromise the model's integrity and hide malicious activities deep within the model's resulting weights.
One of the major tensions I see for enterprises adopting AI is this risk of data commingling. Organizations want to leverage all their accumulated internal knowledge to ground their applications, but they have vast amounts of sensitive, potentially regulated data all mixed in.
This is where the governance really meets the technical implementation. The guidance is unequivocal on this. Sensitive data must be sanitized or anonymized before it's incorporated into LLMs.
So you need robust techniques to make sure that even if the model inadvertently memorizes a pattern, it can't reproduce specific private data points.
You got it.
And the document points to differential privacy as a practical mechanism for achieving this, which is fascinating because it's been in use in other contexts for a while.
It has a strong history, yeah. Especially with institutions like the Census Bureau. They use it to protect individual survey responses while still enabling broad statistical analysis.
So how does it work, conceptually?
Conceptually, differential privacy works by injecting a carefully calibrated amount of statistical noise into the dataset. This noise makes it mathematically difficult, almost impossible, for an attacker to determine if any single individual's data point was included in the training set.
So it preserves privacy.
It preserves privacy while still allowing the model to learn the overall patterns and relationships in the data. It's how you leverage the knowledge without leveraging the PII.
That's a sophisticated defense. But data protection also applies much later in the process to the input phase itself.
Yeah.
The prompts.
Yes. We need to talk about limiting sensitive prompt content.
This feels like something that's often overlooked.
It is. We focus so much on protecting the model itself, we forget that the inputs, the prompts, are often the most sensitive part of the interaction. Attackers who gain unauthorized access to an organization's prompt history can infer massive amounts of sensitive information.
Even if they never touch the model's weights.
Right.
What kind of information are we talking about here?
We're talking about internal business processes, proprietary data definitions, the underlying logic that's driving decision-making, or even highly confidential PII that a user is seeking advice on.
Could you give an example?
Sure. If a finance team is prompting an LLM about complex tax law concerning a potential merger, the prompt itself reveals the merger, the involved parties, and the high-level financial strategy.
The prompt reveals the organization's intent and its proprietary context.
Exactly. So the recommendation is straightforward, but critical for developers to hear. Avoid including sensitive or confidential information in prompts whenever possible. If the model can function without knowing the specific names of the clients or the exact internal metric, you should abstract or remove that sensitive detail to minimize the data exposure risk.
So once we've secured the data, we move to deployment. And here, organizations face these critical architectural choices about hosting your models.
Local or third-party cloud.
Right. And these are decisions that security teams have to vet rigorously because the trade-offs are significant.
Let's assess the model hosting options. You've got local versus SaaS. Local hosting is immediately appealing for organizations with high data privacy or regulatory requirements.
So if sharing data with any external third party is a non-starter, local hosting gives you the maximum control.
Total control. But that control comes with some serious baggage, doesn't it?
It does. The primary trade-off is the cost and complexity of the hardware. You need significant, dedicated processing power, we're talking specialized GPUs, to run and manage those models effectively.
And not only that, but locally hosted models, especially if they're open source or maybe older versions, may deliver significantly weaker reasoning performance compared to the sophisticated frontier models offered by the major cloud providers.
So you sacrifice potential capability for total control.
You do.
Okay, on the flip side, you have cloud or SaaS hosting. It offers seamless integration, especially if an organization's data is already sitting in that cloud environment. But here, the security requirement moves heavily into the legal and compliance domain.
That's the critical requirement. When you hand over your inference traffic, you have to codify legal expectations in your contracts.
You need explicit, written answers to some tough questions.
Yes, like, will the provider use the inputs or logs for future model training or refinement? If they claim not to, how are the logs, which contain your sensitive prompts, controlled, stored, and accessed?
These are questions that require heavy legal and compliance vetting, not just a technical checklist from the security team.
Absolutely.
Speaking of technical choices, let's look at the developer's desktop. The Integrated Development Environments, or IDEs.
Right, where developers spend all their time.
And they are now packed with LLM features.
And the security challenge in IDEs is a form of shadow AI. Tools like VS Code extensions, Windsurf, or Cursor offer massive productivity boosts via LLM integration. They help developers write code faster.
But this convenience is a massive security risk.
A huge risk. Developers can inadvertently expose the organization's proprietary algorithms, internal models, API keys, and sensitive data sets simply by submitting them in an invisible prompt to that integrated LLM for review or completion.
They are essentially leaking the company's crown jewels line by line without ever realizing they are crossing the perimeter.
Precisely. The mitigation here is clear and very specific. Organizations must prioritize IDEs that offer local-only LLM integrations
to ensure that sensitive proprietary data and code remain within the company's environment.
Exactly. It should never be transmitted outside just for a code suggestion.
We also need to revisit R versus fine-tuning in the context of deployment, specifically when it comes to access control.
This is a classic architectural trap. Some organizations will try to fine-tune a model to bake in access restrictions.
What would that look like?
For example, teaching the model to refuse certain sensitive queries if the user ID is labeled customer, but allow them if the ID is employee.
So trying to build the logic into the model itself.
Right. And the guidance strongly warns that implementing these granular controls within the LLM itself is extremely error-prone, it's fragile, and it's often easily subverted by adversarial prompts.
So relying on the model's internal alignment or its training to enforce access rights is a flawed strategy.
It's destined to fail. The wiser, more robust approach is the RAG architecture combined with strict access control lists, or ACLs, applied at the retrieval system level.
So the model doesn't enforce the access, the system that feeds the model enforces it.
Yes. The vector retrieval system checks the user's ACLs before it pulls context from the vector DB. This eliminates the need to implement those complex, failure-prone guardrails inside the LLM.
And it also helps limit hallucinations, I imagine.
It does, by grounding the model in only the authorized, trusted data.
Another key deployment risk involves function calling and the rise of agentic systems.
Function calling is the model's ability to interact with the outside world, to execute code, to call APIs, to send messages.
And if this isn't tightly controlled and scoped,
the model can invoke external actions far beyond its intended purpose. This can lead to unauthorized data changes or, worse, lateral movement and system compromise.
So the actionable step is strict scoping and constant monitoring. We have to limit access to critical functions and ensure the agent or model can only execute the minimal set of actions required for its task.
Absolutely. But maybe the most serious deployment risk the document addresses is the danger inherent in using public models from places like Hugging Face.
Okay, let's dedicate some time here. This is where supply chain risk really enters the AI domain in a very technical way.
It does. The guidance identifies 3 major threats here, starting with malicious packages.
So this is about the delivery system itself.
Exactly. The file formats used to share models, like the Python pickle format, can be abused. The document specifically references the pickle file attack vulnerability.
How did that work?
An attacker doesn't even need to tamper with the model's weights. They just embed malicious code into the package wrapper. That code executes immediately when the model is unpacked or loaded into your environment.
So you think you're getting intelligence, but you're actually executing arbitrary, dangerous code in your machine.
You got it. It's a classic software supply chain attack, but applied to the data science community.
And the second threat is far more subtle. It involves architectural backdoors.
This is the sleeper agent threat. It's really insidious. Bad actors can deliberately create models that have architectural backdoors designed to invert specific malicious behaviors, but only when they receive a specific, often highly obscure, input trigger.
And the research from Anthropic on sleeper agents highlighted that once these backdoors are in there, they're really hard to get out.
They're incredibly robust. They are difficult, if not impossible, to reliably remove through standard fine-tuning or even intensive safety training methods.
Wait, if you can't fine-tune the malicious behavior out, what does that mean for an organization that has accidentally incorporated a sleeper agent model? Do you have to just burn the model and start over?
In many cases, yes, that is the safest approach. You can try to quarantine it by strictly limiting its functions or wrapping it in very aggressive guardrails, but you can never fully trust it. The problem is deep within the architecture itself.
Which requires extreme caution. And that leads us to the third vulnerability here, developer blind spots,
The human element.
where the human element meets the trust problem.
Developers pulling these public models are hyper-focused on the use case getting the model to perform the function they need. The guidance notes, quite bluntly, that developers are notoriously bad at threat modeling and abuse cases.
So when you import a model from an unknown data scientist on a public repository, you are implicitly trusting that person to have considered every possible exploit and built the model flawlessly.
Which is a massive assumption of trust that you just can't justify in enterprise security.
So what's the mitigation strategy for this triple threat of supply chain risk?
It has to be a multifaceted approach. First, organizations must adopt a policy of manually red teaming all imported models. Look specifically for embedded malicious behavior or unintended capabilities.
Second, establish an internal model garden.
Yes, a repository of only vetted, approved models that developers can pull from. And third, and most importantly, red team the solutions that are built with these models. You have to test for abuse cases and align closely with OSB's AI supply chain guidance.
The final deployment risk mentioned is the act of sharing the trained model itself. We love open source, but the document suggests caution when you're distributing a model that's relied upon for critical security or operational decisions.
It's all about limiting the attacker's ability to probe. Giving an attacker a copy of your trained model is like giving them the executable binary of your proprietary software.
It allows them to experiment in a controlled environment offline.
Right. To understand exactly how to cause it to misbehave, what inputs cause failure, and how to find those adversarial examples.
We see that in the high-profile research examples, like the findings that small stickers can cause self-driving vehicles to misidentify stop signs.
Those findings required access to the trained neural network. If your model is responsible for a critical function like fraud detection or operational integrity sharing, that trained artifact unnecessarily introduces significant avoidable risk. You're just giving the attacker a perfect test bed. So deployment locks down the model's home. Inference security is about protecting the model in use.
The actual interaction moment.
Right, from adversarial manipulation. This section focuses heavily on the dynamic controls, input and output validation, and those crucial guardrails.
LLM guardrails have become a buzzword. These are the rules meant to define the model's boundaries, how it should respond, or, more often, what it should absolutely refuse to respond to. How should organizations approach implementing them?
Guardrails are a necessary tactical defense, and they can be layered, they can be manual, explicitly checking prompts and responses for forbidden words.
Simple keyword filtering.
Right. They can be provider-built, leveraging features from cloud services like AWS Bedrock, or they can involve a secondary LLM passing the input and the subsequent output to a third trusted model designed solely to detect trickery and malfeasance.
That seems robust, but the guidance emphasizes a really critical caveat about guardrails.
The caveat is this. Guardrails are not a primary defense. They're secondary, fallible mitigations. Bad actors are extremely skilled and persistent at finding creative bypasses jailbreaks.
So if the information or function is truly sensitive and should never be disclosed or executed,
you cannot rely solely on a fallible guardrail to stop it. The primary defense must be architectural. Ensure the model never has access to that critical function or sensitive data in the first place.
eliminate the risk rather than trying to filter it out.
Exactly.
That principle of defense in depth brings us to the core defense against the most common attack, which is prompt injection. How do we sanitize, validate, and filter LLM inputs and prompts effectively?
Prompt injection is the equivalent of SQL injection for LLMs. It requires a multi-layered approach because the attacker is trying to trick the model into overriding its system instructions.
So what does that look like in practice?
All user-supplied prompts must be pre-processed before they are sent for inference. And if RRED is involved, which adds retrieved context to the user's prompt, you need an additional layer of filtering and validation after that context augmentation has occurred, but before it hits the model.
So you're checking the user input, the retrieved data, and the combination of the two. That's input control. But output handling is equally vital. We need to sanitize, validate, and filter LLM outputs and responses.
Absolutely. The entire goal of prompt injection is to cause intentional misuse or abuse resulting in undesirable behavior. And given the complexity of modern LLM applications, which might involve function calls or external web searches, there are multiple layers of output being generated.
And output validation must cover all of them.
All of them. You need to validate the underlying function call request the model generates before it executes, not just the final text the model presents to the user.
And a related advanced technique in multi-user environments is input segregation. Can you clarify how tagging and isolating inputs reduces risk?
Sure. Think of it like a chain of command in an email conversation. When a prompt is composed, it often includes system instructions, retrieve data from the RJ system, and the user's specific query.
Okay.
We have to clearly tag and isolate the user-provided input from the system-generated context. Why? To reduce the risk of indirect prompt injection.
How does that happen?
An attacker might inject malicious instructions into a public document, say an FAQ page, that the RJ system later retrieves and implicitly trusts as system context. If the system can clearly segregate and tag the user input as untrusted and the system context as trusted, it can prevent the malicious code hidden in the trusted document from overriding the system's primary instructions.
As these systems become more capable, they become inherently more complex, which goes against a timeless security principle.
That's right. We have to constantly heed the wisdom of Bruce Schneier. The worst enemy of security is complexity.
So despite the powerful new tools LLMs offer, every application must adhere to the principle of least functionality.
Only offer the absolute minimum functionality required for the task.
And for autonomous systems or agents, that means explicitly defining, limiting, and applying least privilege to the functions and tools they can access. Web search, the API calls, the code interpreters.
The more functionality you expose, the greater the opportunity for an attacker or an unexpected emergent behavior to cause a compromise. You have to limit the agent's worldview and its capabilities.
We also have to recognize how the very richness of modern models expands the attack surface. Let's talk about modality, language, and encoding, starting with modality.
Multimodal models, which can process text, images, and audio, introduce a severe weakness: safety alignment inconsistency. The guidance notes that a model's safety checks can be strong in one modality, like text, but very weak in another, like images.
So an attacker who finds that a specific unsafe text prompt is blocked by text guardrails
Can simply submit that same text as an image. The visual input bypasses the text filter, and the model executes the malicious instruction. It's a very easy way to confuse the system.
And we see similar confusion in language and character sets.
Absolutely. Most safety and alignment mechanisms are trained predominantly on English data. So these multilingual jailbreak challenges occur when prompts use a different language or non-standard Unicode characters.
And this confuses the guardrails.
It does. It reduces their effectiveness and allows the model to provide harmful instructions that would be immediately flagged if they were in English.
And finally, one of the simplest but most effective obfuscation methods is encoding and decoding.
This is pure trickery. Many sophisticated foundation models, even the smaller, faster ones like GPT-4o Mini or Gemini Flash 1.5, can process encoded data like base64, hex, or even Morse code without explicit decoding instructions.
So an adversary can hide a malicious prompt inside a base64 string.
Exactly. The security filters, which are looking for specific keywords in clear text, just see gibberish, but the model internally decodes the string and executes the malicious hidden prompt, successfully bypassing your perimeter defenses.
That's a powerful example of why input validation has to be so deep and multifaceted.
Oh.
Finally, on inference security, we have to ensure we have proper authentication and API usage monitoring.
For any internal or sensitive AI application, you must enforce strong authentication and access controls, and auditing must be enabled by default. Furthermore, API keys must be managed like currency. They have to be securely stored and never, ever hard-coded in applications.
And monitoring usage itself is a crucial detection layer for abuse.
It is. Anomalous spikes in API usage, especially sudden, unexplained volumetric increases, can be a strong indicator of abuse.
Whether it's an attacker trying to brute force a jailbreak or using the endpoint for unauthorized bulk tasks.
Right. So rate limiting is essential to restrict the interaction cadence and mitigate those volumetric attacks. And structurally, your internal training and inference API endpoints should never be public-facing.
We've established these robust inference defenses, but attacks evolve and models drift over time. Effective monitoring is how we ensure that AI systems remain reliable and aligned with their intended behaviors.
Right, this is about continuous assurance. Figure 2 in the guidelines really outlines the best practices for this.
So what's the foundational practice here?
The foundational practice is continuous monitoring across the entire LLM application and the underlying models. You need visibility into both the security posture and the performance reliability of the system.
Because degradation in performance can often indicate a security issue or drift.
Exactly. They're often linked.
So what are the key metrics and logging practices that organizations need to prioritize?
First, track inference refusals. How often the model refuses to answer a prompt based on its safety rules. A sudden drop in refusals could indicate a successful jailbreak or a subversion of the model's guardrails.
And a sudden spike.
A sudden spike might indicate an increase in targeted attacks against your system. Second, for sensitive workloads, comprehensive logging of both prompts and outputs is mandatory.
Why is it so important to log the output?
Logging the outputs for sensitive workloads provides an undeniable audit trail. If a critical decision is made, or if sensitive information is leaked, you have proof of the specific output generated by the AI. This is vital for accountability, for regulatory compliance, and for any post-incident investigation.
And of course, there's a crucial security reminder regarding these logs.
You have to protect them rigorously. Because those audit logs contain user prompts and sometimes highly sensitive model outputs, they themselves become high-value targets for attackers. They have to be treated as sensitive data with high-level access controls and encryption.
Finally, we need to integrate drift monitoring into this assurance process.
Drift monitoring is non-negotiable for AI reliability. It's the continuous tracking of model performance over time to detect two types of deviation.
Okay, what are they?
There is data drift. This means the input data the model receives in production has changed significantly from its training data, making its decisions potentially obsolete or inaccurate.
That's the second type.
Behavioral drift. This means the model's outputs or its alignment have changed over time. This could indicate unintentional degradation or a successful, slow-burn compromise that subtly alters the model's alignment profile.
So continuous tracking helps you catch these changes before they lead to operational failure or a full-blown compromise.
That's the goal.
This brings us to the highest level of control: governance, risk, and compliance, or GRC. We need a structure to align all these AI initiatives with rapidly evolving regulations and to manage the inherent risks responsibly.
Right.
But the guidance starts with a truly provocative statement about risk.
It does. It really challenges the old security mindset. The document suggests that the biggest risk of AI is not using AI.
That's a bold claim.
It is, but it's realistic. Security teams cannot afford to simply prohibit AI use entirely. Not only are technical controls against unsanctioned use trivial to bypass, but the speed of adoption means virtually every successful enterprise product, from customer service to financial analysis, now leverages AI in some way.
So if a competitor is leveraging AI to gain efficiencies, and your enterprise is stuck in a manual process due to an internal ban, the competitive disadvantage becomes existential.
Exactly. The message to the security team is clear. Your mission is to facilitate secure operations, not to dictate strategy. You have to move from banning to securing.
And to manage that responsibility.
The guidance mandates establishing an AI GRC board, or at least integrating AI oversight into the existing GRC framework. This body is crucial for continually reviewing guidance, implementing approved AI usage policies, and ensuring initiatives are aligned with industry standards and legal requirements.
Okay, next, let's discuss visibility and traceability, starting with the AI bomb.
The AI Bill of Materials, or AI BOM, is directly modeled after the Software Bill of Materials, the SBOM. It's designed to provide crucial visibility into the entire AI supply chain.
So it details the datasets, foundational models, dependencies, and code used to create the final product.
Everything. For governance and ensuring reproducibility, the AI BOM is essential.
But just like the trained model we discussed earlier, the AI bomb itself contains information that is useful to an attacker.
This is a profound tension. A detailed AI bomb reveals technical dependencies and the provenance of the training data, which are goldmines for adversaries looking for specific model vulnerabilities or known weak points in datasets.
So, while creating the AI bomb is essential for internal governance,
the guidance urges extreme caution. Organizations must take great care to limit the disclosure of AI bombs externally to avoid handing an attacker the roadmap to their AI system's weaknesses.
this visibility requirement ties directly into the necessity of model registries. What unique security and operational benefits do these centralized repositories provide?
Model registries are the centralized management system for the entire machine learning model lifecycle. They track every version, every dependency, and every piece of training data, which ensures full traceability.
And the security benefits are huge.
Massive. They enforce strict access controls to prevent unauthorized model modifications. They integrate with drift detection mechanisms. They ensure reproducibility for consistency. They provide secure storage for vetted artifacts and metadata. And they integrate directly into CI/CD pipelines to ensure automated security checks before deployment.
They are the single source of truth for every model you run.
They have to be.
Finally, GRC must connect to regulatory frameworks. And the global legal environment is chaotic and changing incredibly fast.
The complexity is enormous. Organizations have to track major global mandates. The guidance highlights several key examples. For instance, the EU's Artificial Intelligence Act establishes a rigorous, risk-based classification system, demanding far stricter controls for high-risk applications.
And in the U.S., we see focused efforts like Executive Order 14110,
which sets national policy goals for safe, secure, and trustworthy AI development,
alongside more targeted legislation like the ELVIs Act,
which specifically addresses the unauthorized use of AI to replicate voices and likenesses, a growing area of concern for intellectual property and fraud.
And we also see regulations driven by national values, like China's interim measures, which mandate that generative AI aligns with socialist values.
It really illustrates how deeply cultural and political requirements are being codified into technology law.
In addition to these laws, the document emphasizes the non-mandated guidance that is crucial for technical implementation.
Right, things like the SANS AI security controls, the NIST AI risk management framework, and the OWASP Top 10 for LLMs. These frameworks provide the practical how-to, even if they aren't directly codified into law yet.
One final technical governance point the authors make is about system prompts. These are the high-level instructions given to a model to guide its general behavior.
They're quick to update, which makes them appealing.
But speed often means fragility and security.
Precisely. System prompts should only be viewed as a practical, temporary, or incomplete mitigation. They are easily forgotten and often easily subverted.
You must ensure they are never overwritten by user prompts,
which requires those extra guardrail layers we discussed. For significant, lasting alignment changes, fine-tuning or retraining the model may be necessary instead of relying solely on prompt-based alignment, which is an easily exploited shortcut.
So now we enter the realm of autonomous AI. Agentic systems, whether they are simple API chains or complex independent decision-makers, can chain tasks, invoke functions, and act independently across an enterprise.
And this autonomy demands a complete rethinking of how we apply security controls.
What's the defining security risk of these agentic systems?
In a word, scope creep. Because these systems are designed to chain tasks, they may invoke unintended tools, access data they weren't explicitly authorized to use, or generate entirely unpredictable behaviors.
This autonomous action introduces the risk of unintended lateral movement or secondary effects across the enterprise.
And it can potentially move a minor vulnerability into a catastrophic breach.
So we have to apply the principle of least privilege not just to the human user, but to the agent itself. What are the critical controls for managing this new risk?
The document lays out 4. First, we need a defined function scope. You must configure agents with clearly delineated permissions. They should only have access to the absolute minimum set of tools and data required for their specific task.
So if it's a booking agent, it shouldn't have access to the financial ledger.
Exactly. Second, execution isolation. This is all about containment.
So using sandboxing or containerization rigorously?
Yes. This restricts the agent's operating environment. Why is this critical? If the agent is compromised, perhaps through an indirect prompt injection that makes it try to reach a database it shouldn't, the sandboxing prevents that lateral movement and limits the potential impact to that isolated environment. It makes the breach harmless.
Okay, third is API and functional call controls. We have to gate its external actions.
Access to external APIs and critical functions must be gated via strict allow lists. Every agent-initiated request has to be validated at runtime. And crucially, the guidance states that operations with high operational or financial risk must never be exposed without mandatory human oversight and sign-off.
So the agent can suggest the action, but a human has to be the final gate.
A human is the circuit breaker. And fourth, feedback loops and escalation.
What does that mean?
Agents need built-in confidence thresholds. When an agent is uncertain about a decision, or if its activity levels exceed certain parameters that might indicate risk.
Like rapid high-volume tool invocation.
Exactly. It must have predefined fallback mechanisms. It needs to escalate that decision to a human operator for review and intervention, rather than proceeding autonomously into uncertainty.
And continuous monitoring is paramount here for maintaining assurance.
Absolutely. You have to specifically monitor for autonomy-related anomalies. This includes looking for excessive tool invocation, getting caught in task loops, or any deviation from expected outputs or behaviors. Behavioral baselining and anomaly detection are essential for maintaining assurance and containing these powerful systems once they're in production.
We've spent this time building and securing the system, but we have to face reality.
Yeah,
A compromise will occur.
it will.
And traditional incident response, or IR, playbooks are just not sufficient for the unique threats posed by AI. We need AI-specific IR readiness.
We're dealing with entirely new categories of threats that demand dedicated preparation and expertise. These include deep compromises like model poisoning.
Corrupting the integrity of the training data.
Right. Prompt injection, which is manipulating the model during inference. Data leakage through output generation, which is coaxing the model to disclose sensitive training data. And unauthorized model extraction, stealing the highly valuable model parameters themselves.
So the IR requirements have to evolve to cover the entire AI stack, not just the network and the endpoints. What is required for effective incident investigation and containment in this new domain?
There are 4 critical specific requirements. First, you must capture audit trails across the entire stack. This means your logs must cover every piece of the transaction: the initial prompt, the augmentation sources from the vector DB, the model outputs, any function calls, and all external tool invocations.
If you can't reconstruct that full chain of activity, forensic investigation is impossible.
It's impossible. Second, you need indicators that tell you the model itself has been tampered with.
So monitor for model tampering indicator.
Yes. Watch for sudden, subtle shifts in inference behavior changes and output quality, unpredictable drift in responses, or an unexplained increase in refusal rates. These are subtle clues that the model may have been adversarially manipulated or subject to an unauthorized update.
Third, dedicated detection layers for attacks that bypass traditional security.
Exactly. You need detection layers on prompt and output designed specifically for AI attacks. This includes pattern-based and behavioral monitoring, looking for jailbreak attempts or bypasses achieved through those obfuscation methods, like the multilingual prompts or encoding tricks we discussed earlier.
Standard network intrusion tools won't catch these.
Not a chance. You need AI-native detection.
And finally, a mechanism to verify that the core asset hasn't been swapped or corrupted.
Model integrity baseline is essential. You use cryptographic hashes, model registries, and scheduled validation checks to confirm that the deployed model parameters have not been altered. If the calculated hash of the deployed model suddenly differs from the verified baseline, you have immediate proof of a critical integrity compromise.
And all of these updated requirements have to feed into updated playbooks.
The playbooks have to include specific, detailed procedures for how to execute a model rollback, how to revoke access to compromised accounts, how to trigger necessary retraining workflows, and how to revalidate data sources if you suspect poisoning.
And practice is key.
Red teaming exercises and tabletop simulations must be tailored specifically to LLM misuse scenarios, testing the organization's ability to respond to prompt injection or model theft. This practice is crucial for building practical resilience.
We've journeyed through the entire lifecycle of AI security. We moved from foundational requirements like secure access controls and data integrity to the complexity of deployment, understanding the dangers of public models and the need for isolation, and finally addressing the multi-layered defenses required for inference security and autonomous agent governance.
The core takeaway from this extensive collaborative guidance is that AI adoption is not a matter of choice anymore. It's a competitive necessity. The transformative opportunity is vast, but it can only be realized if organizations establish a strong, comprehensive security foundation that respects the unique vulnerabilities of these systems.
Embracing the best practices we discussed, from digitally signing vector DB chunks to implementing rigorous input and output filtering and mandatory human oversight for autonomous agents, is the only way organizations can maintain reliability, ensure trustworthiness, and minimize enterprise risk while successfully leveraging AI innovation.
Right.
This structure really provides a complete blueprint for securely implementing AI that respects both the technology's power and its new complex threats.
And this journey highlights a fundamental conflict that listeners are going to face as regulators catch up, and it's this. If organizations must limit the disclosure of detailed AI bombs because the technical dependencies and data provenance contain attack information useful to adversaries, how will regulatory bodies balance their need for transparent supply chain accountability with the practical security risks posed by deep visibility into those model dependencies?
That's a great question.
That tension between compliance and practical security is the critical challenge you must be prepared to navigate in the coming decade.